Welcome to today's presentation on the bias variance trade-off in regression analysis. It's a famous topic, and today I will show you a numerical example on how to work with it. But we start with a quote: "Computer cannot replace man." It's a famous quote, but who said it? Actually, the original is from It's a Cannibal Wisdom. This is a famous graph from the book of Hastings, Dipshon, and Friedman, which depicts the training error and the test error. And as we know, as model complexity goes up, training error goes down, but the test error initially goes down, then goes up. And we look for the complexity level at which the test error is minimal, and this is called the best trade-off between bias and variance. And today we'll see numerical example. We'll make this graph with numerical values, and we will see that when the model is unbiased, so when the bias is 0, we'll see what this means, then this model is never optimal. So we start with a very simple example. We have a data set of green balls. We would like to predict the size of next ball. From this data set, one possibility is to use the average in the data set among the green balls. Another possibility is to say I would like to use a little bit smaller than the average among the greens in order to predict the next balls. Which one we will use for prediction? It will turn out that this one is much better, although the optimal one is the average of the green balls in the population of green balls, not just in the data set that we have at hand. So if this black one is the true average of the green balls, it will have the smallest error, and the error we count as the size of our prediction minus the size of the next ball squared, and so on. So we have this for all test balls, and we have the average squared error. For regression, we use squared error to minimize, which we minimize, and this is how we count the test error, with the squared error loss. So it's the average of the squared errors over the test set where the test set is infinite, so the test set is actually equal to the population. Now, what is the example at hand? Toss a die. The average value in the population is 3.5. This will be our optimal prediction. However, if we have a data set of just 2 tosses, what can we do? We can say we would like to predict the average, which we know is 3.5, from these tosses, and this will be the average of the 2 tosses on the left, or average in the data set, but times 0.99, which is a very strange number, but let's see if it will work. This is for homework. Here in this video, we'll do only 1 toss. The data set consists of just 1 toss. So, for example, if we toss 2, our prediction is the average in the data set, which is 2. Future tosses are from 1 to 6, occurring with equal probability, and the average error on the future tosses is, in this case, 5.1667. We count the error as squared error. So the best prediction is 3.5. Whatever is the data set, we know this is the best prediction, and it will give an error of 2.9167. Just note that the error of the best model is not 0, just because the future tosses are different values, and our prediction must be only 1 value. So what is the setup when we have the data set that consists of 1 toss? What would be the expected error? Our prediction is the same as we see. Future tosses are from 1 to 6. So each data set occurs with equal probability. And for the first data set, our loss is 9.1667. For the last data set is the same. So on average, we have 5.8333. We take the average because each data set is equally likely to occur. And this is our expected test error before we toss. So before we toss, when we toss, it will be one of these 6 errors, but before we toss, all of them are equally likely. So our expected loss is 5.8333. However, if we multiply our prediction by 0.99 times the average in the dataset, we get these possible errors, and the average is 5.77, and it is lower than 5.83. And this is by no means by chance. This is due to the bias variance trade-off. It's valid for all possible numbers, data sets that you can check, except 2 cases that we'll discuss in the end, which are trivial and never occur in statistical learning. So how come when we predict not the average in the data set, but something else, so 0.99 times the average in data set, we get better prediction from squared error loss on the test set? It's very strange. Now, let's see what is the best coefficient by which to multiply the prediction. It's called penalization coefficient. In this case, for the toss a die example, it's 0.8. And the expected error is 5.27. Very interesting. So we can do that for different coefficients and see what is the test error. And it turns out that when the test error is between 0.6 and 1, it is lower than when the coefficient is 1, which is a big bend for this data set. And the minimal occurs at about 0.8, it was 0.8077. So even if we don't know what would be the best coefficient, if we take 0.99, it yielded a better result. One interesting observation is that when the coefficient is 1, when we move away from it down, when we reduce it a little bit, we always have an improvement. And when the coefficient is 1, we have unbiased model, as we'll see in a minute. So when we move a little bit away from the unbiased model, we already have an improvement, and this always occurs. So a small deviation from biased model results in smaller test error, and one definition, the deviation from unbiased model is called penalization. Actually, it's deviation to the left. Now let's return to our example. We saw that when we multiply by 0.615, we get exactly the same error, which is a little bit unlogical because you almost like multiply by a half what you see, and you have the same error, which is very, very strange for this example, but it's true. Now let's see the summary. Test error is the same in both these very different cases. Now we see how this is connected to bias and variance. So the average prediction over data sets is 3.5. This happens to be the average in the population. Therefore, we have unbiased model. So it means that the average prediction among different data sets is equal to the average in the population. The average of predictions over data sets in the second case is 2.15, the true average 3.5. Therefore, we of course have a biased model, and the bias is equal to minus 1.34. And the average of our predictions is actually 3.5 times 0.1654. Therefore, it cannot be equal to 3.5. What about the variance? The variance of the predictions is equal, in the first case, 2.91. In the second case, 1.10, much smaller. So what happened in the end? We have bias variance. First case, bias variance. Second case, the bias went up in absolute terms, the variance went down. We will see that this bias variance trade-off, here is how it occurs. So if bias goes up, the variance will go down, but always the variance win in the beginning. So there is no model with bias equals 0 that is optimal. We will see this in a minute. So the test error, the squared test error, can be decomposed into bias squared plus the variance of the predictions plus the variance of the population values, which is known as noise. In our case, when the prediction is equal to the toss value, we have that the test error is, so bias squared, 0, plus variance of the predictions, plus noise. So variance is a shorthand for variance of the predictions of our model over different training sets. So in this case, the test error is 583, and when we have coefficient times the toss value, we see what is the test error, and now we can plot it for different coefficients. And here is what happens. The test error, we saw it already, the blue one. The green one is the training error. The training error is just the squared error between our prediction and the variance and bias. So variance goes up, bias goes down. This is why we have a trade-off between the two. And we arrive at what we wanted to arrive at, the graph on the left in the book, and the one on the right. If we remove bias and variance, we get exactly what we needed. So the training error goes down and the test error goes down with a numerical example. And in our numerical example, the best trade-off is at around 0.8. What about if we toss 2 dice? Then the training error goes or looks a little bit different, and the best trade-off goes a little bit closer to 1. So the bigger the training set, the closer to 1 is our optimal coefficient, and it will be 1. So when coefficient optimal is 1, it will be 1 when our training set is actually the population. But in this case, we just compute the average. We don't have to estimate it. Or in another case, optimal is 1 when the population consists of only one number that repeats, for example, 3. So we don't need any learning. We just know that it's 3, and in every data set it's 3. The average is 3. So we don't need any penalization. But this means that there is no noise in the data. And in machine learning and statistics, we're not interested in such data sets. So these are the derivations for the graph here on the right, with the training error and test error when we toss 2 dice. So we have data set for the first 2 columns. We have prediction, we have future points, we have test error, and the prediction on the left side is the average in data set. This will be unbiased model, and on the right, prediction is the average in data set times 0.89362, which happens to be the optimal prediction. And you see that the test error is lower for this prediction level. So this corresponds to the red line on the right. Now, how did we come up with this penalization factor 0.89 in this case? So let's see one derivation. We have mu is the average, mu hat are our predictions over data sets. Unbiased predictor, which means that the expected value of our predictions over data sets is equal to the true mu. So expected value of mu hat is equal to mu. And y are future observations. Mean square error, we know that what that means. It is how our predictor varies with the average. However, we are interested in the test error, which is how our predictor, which is mu hat or alpha mu hat in the penalization case, is different from y. This is the difference between prediction and test points. And in the first case, for the mean square error, we have one expected term, because mu hat is moving, mu is fixed at 3.5. And for the test error, both y's and mu hat vary. Therefore, we have double expected sign. So when you fix mu hat, still y varies. So we have expected value over y. Y are the test points, infinite many test points, which is actually y comprises the whole population. So both m and y vary. M hat varies over data sets, and y, they are just the future observations. And the test error decomposition is actually the test error is equal to the mean square error plus variance of y, which is known as noise. And the mean square error is decomposed into bias square plus variance. Here we see it. And we would like to minimize the test error, of course. How do we minimize it with respect to alpha? We take the derivative, just one line of derivation. We set it to 0. Turns out alpha is equal to mu squared divided by mu squared plus variance of mu hat, which means that alpha is greater than 0, but also means that alpha is less than 1. So alpha is 1 only when variance mu hat is equal to 0, which again occurs when our mu hats are the same over training sets. And this occurs when the training sets, all of them are the population, so we have the same prediction, or when the training sets are all the same, which means that there is no variation in data, and both cases are not interesting. So this is alpha, but we cannot compute it because it's theoretical. We cannot compute it because mu is unknown. So if you know mu, we don't have to compute alpha. We're looking for mu, we'll just know it right away. But here we just see that when we have unbiased estimator, we always have to penalize it. We don't know how much, but we know that we have to penalize it. And this now unleashes a myriad of regression techniques from neural networks, support vector regression, ordinary least squares, etc., that try to find, penalized OLS like rich regressions that try to find this optimal alpha, where they introduce penalization coefficients that reduce our mu hat, our predictions. They make them smaller, closer to 0 in absolute terms, just to be able to find this optimal alpha in different ways. So myriad of techniques emerge to approximate this alpha that we test with cross validation, but this is for another topic. What could be the optimal alpha for each regression technique? Now, for those of you who are not very handy with taking derivatives when we have expected values, here is exactly the same situation. When instead of expected values, I've written sums. So the I is the sum over future points. They go from 1 to n, and is, let's say, infinity. And the data sets are from 1 to 6. Well, they can go more than 6, but they are just 6 different data sets that occur with the same probability. So when we take the derivative of this term with the two sums, we get exactly the same answer for alpha. What happens when we have regression analysis with different x's? So now we could think of that we had different y's from 1 to 6 for a particular x, but we could have different x values and different y's. So we minimize the squared test error over all these x points. So in this case, there are n points. We take the derivative with respect to alpha, and we again come up with what is the penalization parameter, the optimal one for regression. For regression when we have different y's at different x's, and we only assume here that we want to have an unbiased model, as you see on the right. So expected value of mu hat for each x is equal to the mu x. So this is it. So we are penalizing unbiased model. No other assumptions, no normality of errors, nothing. Errors could be random, doesn't matter. The only thing that matters is that we use quadratic squared error, and everything is written on this slide. What we need to know to compute the optimal alpha, and the optimal alpha is equal to this ratio that is again between 0 and 1. One interesting case for OLS, if it is unbiased, how do we bias it in an optimal way? is with this alpha that is at the end. And the interesting thing is the term with the variance of mu hat x, and the sum of all variances over x is equal to p over n times sigma square, where sigma square is the variance of the y at x. It's assumed to be the same, the variance over all x, and this term is p over n times sigma square, and p is interestingly called the degrees of freedom. P is equal to the number of inputs, and this p and true alpha is connected to a lot of criteria for penalizing OLS, like Schwarz, Akaike information criteria, and even R-square adjusted. Just one last point: when we have a penalized OLS, what we do is that we take the prediction from the OLS line, which is the blue line. We multiply the blue by alpha. We make it closer to 0, and this will be our more optimal model than the OLS for predicting future points. So always our predictions go down. So our predictions are mu hat, and they go down. They are multiplied by alpha times mu hat. For example, in ridge regression or lasso or others support vector machines, we are pushing down this line by making the coefficient of it smaller, which is exactly the same as pushing the y's down. We either push the coefficients down or y itself. So this concludes the talk. I hope it was interesting.